You know the feeling, right? You open up a spreadsheet or a database and it's just a mess. It's totally out of control. Well, today we are going to tackle that chaos head on. We're talking about database normalization, which is really just a fancy term for the art of bringing some beautiful, logical order to your data.
So, have you ever been in that spot where you go to update one tiny little thing in a spreadsheet and suddenly everything breaks? Or you find yourself having to manually change like 10 other cells just to keep things consistent? Yeah, it's super frustrating, and it's a huge clue that there's a problem with how the data is structured in the first place.
I mean, just look at this table. The head of department, Mr. X, and his office number are copied over and over and over again for every single student. This is what we call data redundancy, and it's a time bomb. Just imagine Mr. X gets a new phone number. You'd have to hunt down every single one of these rows to update it. And if you miss just one, boom, your data is now inconsistent, it's unreliable. This is exactly the kind of chaos we're here to fix.
And thankfully, the solution to all this mess has a name: normalization. The best way to think about it is like a methodical, step-by-step process for tidying up your data. We're going to take these big, messy tables and organize them into smaller, much cleaner, and well-structured ones. The whole point is to get rid of that repetition and make our data trustworthy and just plain easier to manage.
Okay, so where do we even begin? Well, this whole tidying up process happens in stages or forms. Let's start our journey with the very first and maybe the most fundamental rule of all.
And that brings us to the first normal form, or 1NF. Honestly, the rule couldn't be simpler. Every single cell in your table can only hold one single piece of information. That's it. When you hear the word atomic, just think indivisible. It can't be broken down any further. One cell, one value. That's the whole rule.
This table right here is a perfect example of what not to do. Just look at that EMP skills column. John Tech has Python, JavaScript, all stuffed into one cell. I mean, how are you supposed to easily find everyone who knows JavaScript? It's a nightmare to search, it's a pain to update, it's just messy. This table is breaking the rules of 1NF.
So how do we fix it? We break it up. We decompose the original table into two. The first one holds the employee's main info. The second one is brand new, just for their skills, and we link them together using the employee's ID. Now look at that. Each skill gets its very own row. Every single cell holds a single atomic value. Now the data is clean, it's searchable, and it is officially in first normal form.
All right, so far so good. We've gotten rid of those repeating groups, and all our data is atomic. But you know, our tables can still have some sneaky, hidden problems. So for our next step, we're going to build on what we just did and tackle something called a partial dependency. This is going to give our data a much more stable foundation.
Let's talk about second normal form, or 2NF. This rule has two parts. First, your table absolutely must already be in 1NF. And second, and this is the key part, every other piece of information in that table has to depend on the entire primary key, not just a piece of it. This rule really only matters when your key is made up of more than one column, what we call a composite key.
So, the problem we're trying to solve here is called a partial dependency. Think of it this way. You have a piece of information that's only hanging on to a piece of the main ID, not the whole thing. It's like knowing a street name but not the city. The relationship is unstable and incomplete. We need every bit of data to be fully dependent on the entire key.
Okay, let's look at this example. To uniquely identify a row, we need both the teacher_ID and the subject. That's our composite key. But now, what about the teacher_age? Does a teacher's age depend on the subject they teach? No, of course not. It only depends on their ID. That right there is a partial dependency, and it's what's causing the age 30 to be repeated for no good reason.
Fixing this is actually a really clear three-step recipe. First, we spot that partial dependency, in this case, the teacher's age. Second, we take that column and we move it out into its own brand new table. And finally, we link that new table back using the part of the key it actually depends on, which is just the teacher ID.
And check out the result. We've got a teacher detail table where each teacher's age is stored just one time. Perfect. And we have a teacher subject table that cleanly links teachers to their subjects. No more repeated age data. It's way cleaner, way more efficient. We are now officially in 2NF.
We are on a roll. We've handled single values, we've dealt with partial dependencies. Now it's time for the third, and for most database designs anyway, the final major step. This is what gets us to the gold standard of data tidiness.
And this is third normal form, or 3NF. The rule here is pretty straightforward. First, you have to be in 2NF. And second, you have to make sure that every column that isn't the key depends directly on the primary key and on nothing else. There are no middlemen, no indirect dependencies allowed.
What we're hunting for here is something that acts like a chain reaction. It's like a game of telephone. The primary key determines column A, but then column A turns around and determines column B. See? Column B doesn't depend directly on the key. This indirect relationship is called a transitive dependency, and our job in 3NF is to find that chain and break it.
So in this table, our main key is the EMP_ID, and the EMP_ID correctly tells us the employee's name and their zip code. But now look at the state and the city. Do those depend on the employee? Not really. They depend on the zip code. If we had 10 employees living in Noida, we'd be repeating UP in Noida 10 times. That's the exact chain reaction we need to stop.
And you know what? The fix follows the exact same logic as before. First, we find that indirect dependency, the city and state depending on the zip. Then, we move them out to their own new table. And finally, we make the column they were depending on, the EMP_zip, the primary key of that new table. It's a pattern.
And there we go. The chain is broken. We have two beautifully structured tables. The employee table simply tells us which employee lives in which zip code. And the new employee_zip table is a perfect little lookup for finding the city and state for any given zip. Every piece of information is stored only once. This is 3NF. So, we've walked through the three main stages of normalization. And, it seems like a lot of work, splitting up all these tables. The question is it always worth it? Let's take a quick look at the big picture, the benefits, and, the trade-offs. The advantages are massive. You get rid of almost all the data repetition, you make sure your data stays consistent, and you build a really flexible database that's way easier to update. But there is a flip side. Having lots of separate tables can mean your database has to work a little harder to join them all back together, which can sometimes slow things down. It also means you really need to do some careful planning up front.
And hey, just so you know, the journey doesn't technically end at 3NF. There are even higher normal forms out there, with names like BCNF, 4NF, and 5NF. But honestly, you can think of those as highly specialized tools for really complex academic-level problems. For the vast majority of stuff you'll ever build, getting to third normal form is the goal, and it'll give you a fantastic, solid design.
And that kind of leaves us with a final, interesting thought. Normalization gives us this perfectly organized, beautifully consistent database. But in today's world, where we're often obsessed with raw speed and analyzing gigantic datasets, sometimes a little bit of planned redundancy is actually okay if it makes things faster. So the big question is perfect organization always the ultimate goal? Well, that's something every single database designer has to figure out for themselves.